Welcome you all to the new session of Control System 1. Today we'll be discussing about basics of signal flow graphs. So what is signal flow graph? What are the basic terminologies associated with signal flow graphs? How to construct signal flow graph from describing equations? All this will be discussed in this lesson. So before starting, let me recapitulate last few classes on block diagram reduction technique. So the purpose of block diagram reduction technique, as you all know now, is to determine overall transfer function of a system so that the system can be analyzed based on transfer function based approach. Now, determination of transfer function using block diagram reduction technique is an effective method, but having some drawbacks of that technique. What are those drawbacks? For very complex control systems, sometimes it is cumbersome or difficult to use block diagram reduction technique to determine overall transfer function. So our main objective in block diagram reduction technique was to represent a system, whether it is simple or complex, using block diagrams. And later we discussed about block diagram reduction technique, different rules associated with it, so that we can get overall transfer function of a particular system described by block diagram. But as for very complex control systems, it is difficult to determine overall transfer function using block diagram reduction technique. That is why we may opt for signal flow graphs based uh, transfer function determination, which is much easier compared to block diagram reduction technique. So what are the basics of signal flow graphs? That will be discussed in today's class. So let us start with the next slide. In this slide, here we have written few topics which are to be covered in today's lesson. So first one is, what is SFG or signal flow graph? SFG stands for signal flow graph. What are the basic terminologies associated with SFG or signal flow graph? Next, will be discussed about basic rules of SFG simplification, such as if two signals are in parallel, then how to simplify those, as like block diagram reduction technique rules. If two are connected in cascade or back to back or series, then how to simplify. Those rules will be discussed under this topic. And last one is construction of SFG from governing equation. That means, as I already said in previous classes, a system may be represented in various ways, such as by circuit diagram, schematic diagram, phasor diagram, mathematical equation, block diagram, state space representation, etc. So, as we know, any physical system can be represented by its governing equation. So, if a system is represented by its governing equation, and if that system's transfer function is to be obtained, then we must know how to construct signal flow graph from a governing equation so that we can get overall transfer function of that particular system. So these are the topics which are to be covered under today's lesson. So let us now move to next slide. What is SFG? So first we'll discuss what is signal flow graph, or why shall we study signal flow graph. The purpose of studying signal flow graph serves the same purpose as block diagram reduction technique does. That means block diagram reduction technique and signal flow graphs both are used to determine overall transfer function of a system. But block diagram reduction technique sometimes is difficult to apply for very complex system. In order to reduce that complexity associated with block diagram reduction technique, in order to determine overall transfer function of a particular system, we must opt for signal flow graphs. So signal flow graph based approach is a substitute of block diagram reduction technique. Both signal flow graphs and block diagram reduction technique serve the same purpose, that is to determine overall transfer function of a system. Now, what is SFG? Signal flow graph is an alternative method, as I said, of block diagram reduction technique for determination of overall transmittance or transfer function of a complex system. So a new term came here, that is transmittance. So what is transmittance? Transmittance is nothing but transfer function of a system. Most of the cases we use transfer function, but in signal flow graph we use transmittance instead of transfer function. So both are same. Somewhere it is called as transfer function, and in SFG the transfer function is termed as transmittance. So signal flow graph, as the name implies, it's a graph which is associated with some signals, and flow means in which direction the signal is flowing, or in which direction signal is being carried out, is given by some arrows. So signal flow graph is a directed graph. It is associated with some signals which are having some specific direction. Signal flow graph consists of different nodes, directed branches. As I said, branches means signals. Signals will be flowing from one direction to another direction with path gain. Suppose, let us go to next slide. See here, this is a signal flow graph. This one is a signal flow graph in which it is having some nodes x1, x2, x3, all this, and some branches, x1, x2 branch, x2, x3 branch, x2, x4 branch, x3, x3 branch, x3, x4 branch, x3, x2 branch. So all these are branches. Now see, all these branches, x1, x2 branch is associated with a path transfer function of a21. Similarly, x2, x4 branch is associated with a42 transmittance or path gain. So these are path gains. These are branches. These are nodes. Likewise. So these are the basics of signal flow graph. What a signal flow graph should consist of is given here. Next point is Mason's gain formula is used to determine overall transmittance of a system represented by SFG. That means a formula named as Mason's gain formula. It's a very effective formula which is being used to determine overall transmittance from signal flow graph. So if signal flow graph is given to us and we are asked to obtain overall transmittance, we must apply Mason's gain formula in order to get the overall transmittance. Now see, a system may be represented by block diagram, may be represented by its mathematical equation. Whatever the system representation is, we may use Mason's gain formula. How? Because later you'll be seeing that how to draw signal flow graph from block diagram. So if you know how to draw signal flow graph from block diagram, and if you know Mason's gain formula for a particular SFG, then you can get overall transfer function or transmittance from a block diagram using Mason's gain formula. So there are two parts. One is whatever the system representation is, first convert it into SFG. Once SFG is obtained for that particular system, you must use Mason's gain formula to get that overall transmittance. Now let us move to next slide. This slide discusses about basic terminologies associated with SFG. Now see, as I said, the first basic terminology is node. Node is system variables. That is x1, x2, x3, x4. So x1, x2, x3 and x4. These are four nodes. Now, in between any two nodes, x1, x2 or x2, x4 or x2, x3 or x3, x2, in between any two nodes, there is a line joining those two nodes. These lines are joining any two nodes. So these are termed as branches. What is gain? These are gain. These are gain of that path, or this is known as path transmittance. So gain means weight or transfer function associated with that branch, such as A21, A23, all this. Next, input or output node. Input and output node. First, let us discuss about input node or source node. See, this X1 is having only outgoing branch. No branch is entering at X1. So the branches which are having only outgoing branch, the nodes which are having only outgoing branches are known as input node or source node. So nodes having only outgoing branches such as X1. But X4 is outgoing output or sync node. Why? Because it is syncing all the branches. It is not producing any branch. So the the node which is having only incoming branches are known as output nodes, such as X4. X4 is having only incoming branches. There is no outgoing branch from X4. That is why it is termed as output node. So what are these X2, X3? It is not mentioned here, but let me tell you, X2 and X3 are termed as intermediate node, which are having incoming, outgoing, both the branches. Clear? Okay. So let us now move to next slide. These are few other terminologies associated with SFG. What is forward path? Path from input to output. See, this is one path marked by this red line, which is a path from input node to output node. So this is one forward path. Similarly, there is another forward path. Let us mark it by pink. This is another forward path connecting input node and output node. So there are two forward paths in this figure. One is shown by red line. One is shown by this red line. another is shown by the pink line. Both for both the paths, see here, it is connecting input node with the output node. So the possible paths which can connect input node to output node are known as forward paths, such as x1, x2, x3, x4, shown by red. x1, x2, x3, x4. This is one forward path. Another forward path is x1, x2, x4. Another forward path is x1, x2, x4. So these are forward path. So note that these forward paths are given in terms of nodes, but forward path gain is gain of a particular forward path. As we saw here, there are two forward paths. One is this one. So what would be path gain for this forward path? Path gain for this forward path is A21, A32, A43. So this is one forward path gain. Path gain associated with first forward path. Another forward path is, this is another forward path which is having path gain of A21, A42. So this is difference between forward path and forward path gain. Forward paths are associated with nodes, whereas path gains are associated with gain of that particular path. Next is loop or feedback path. See here, x2, x3, again x2. This is one loop. So a closed path which originates and terminates at same point is known as a loop or feedback path. So see here, this started at x2, this loop started at x2, flows through x3 and returns back again to x2. So this is known as one loop, x2, x3, x2. Now what should be gain of this loop? Gain of this loop will be a32 into a23. So this is the loop gain. So as like forward path gain, loop gain will also be associated with the path transmittance, whereas loop or feedback path will be associated with the nodes. This one involves only one node. Starting from one node, there is no other intermediate node, and ending at the same node. This is known as self loop, and gain of this self loop is a33. Let us now move to next slide. This slide tells us about basic simplification of SFG. See here, these are three nodes. Now these three nodes are joined together through these lines. So these lines are having A and B path transmittance. So what would be overall transmittance between input node X and output node Z? As these are connected in series or back to back, as like block diagram reduction technique, this will be multiplied together. Both the transmittance will be multiplied together to get overall transmittance. So in between X and Z, there is overall transmittance of AB. Similarly, if branches are in parallel, see, two parallel branches are there in between two nodes. One is having A transmittance, another is having B transmittance. So as like block diagram algebra, these two transmittance will be added up to make parallel combination. Similarly, For isolated loop or feedback path, see, this is W node, which is input node. This is Z node, which is output node. So in between input node W and output node Z, what will be overall transfer function? See, between W and X, there is A. So between W and X, there is A. X and Y is having two paths. One is forward path from input to output, another is feedback path from output to input. So as like block diagram feedback rule, between X and Y, there will be G by 1 plus GH. And Y and between Y and B, there is B. So now these three are path transmittance having series connection. So overall transfer function will be, overall transmittance will be A multiplied by so these three will be multiplied together to get overall transmittance. So these are the basic rules associated with SFG. Although Masson's gain formula is the single rule which will be applicable anywhere to get solution from SFG. Next, let us discuss all these forward path gains, loops, loop gains, touching loops, non-touching loops, all this with the help of example. Now for consider this SFG, considering this SFG, determine the possible forward path gains, loop gains, non-touching loop gains. Let us find these three for this figure or for this SFG. So what are the forward path gains? How many forward paths are there? It's very simple. Forward, how many forward paths are there? The paths connecting input and output are known as forward paths. So this is one forward path. Is there any other forward path? Yes, there is another forward path, which is this one. So there are two forward paths. Okay. So for first forward path, for this forward path, straight forward path, what is loop gain? G1, G2, G3, G4, G5, G7. So G1, G2, G3, G4, G5, G7. This is one forward path gain. What is another forward path gain? G1, G2, G3, G4, G6, G7. So this is another forward path which is having G1, G2, G3, G4, G6, G7. This forward path gain. Now what is loop gain? What are the loop gains? How many loops are there? See, this is one loop. This is second loop. This is third loop. This is fourth loop. So there are four loops. So for first loop, gain will be G2 H1. So for first loop, loop gain is G2 H1. For second loop, G4 H2, G4 H2. For third loop, this is the third loop, G4 G5 H3, G4 G5 H3. And for fourth loop, again is G4 G6 H3, G4 G6 H3. So these are the loop gains for this SFG. Now, what are the non-touching loops? What do you mean by non-touching or isolated loops? Suppose you have two loops like this. Suppose that you have two loops like this. Now, is there any common part between loop 1 and loop 2? There is no common part. How can you say whether there is any common part or not? Let us mark all the nodes. First loop is A, B, A, and second loop is C, D, C. So these are two loops. Is there any common node or common point? No. That is why these two loops are not touching each other at any point. So these are termed as non-touching loops. Now say, for example, there is another loop here. So the third loop is B, C, D. Now these two loops are not touching each other, but loop 1 and loop 3, loop 1 and loop 3. See here, there is a common point between loop 1 and loop 3, that is B. See, between loop 1 and loop 3, there is a common point B. So these two loops, 1 and 3, are touching each other at point B. That is why we cannot say loop 1 and loop 3 are non-touching. These two are touching loops, and these two loops touch each other at point B. So this is how we can determine which are touching loops and which are non-touching loops. Later, while we will be applying Mason's gain formula to determine overall transmittance, this non-touching loop concept will be required. That is why it is important to understand how to determine touching loops and non-touching loops. I am again telling you that first mark all the all the nodes, and later describe all the loops in terms of nodes like this. All the loops are being described by in terms of nodes. Now, if there is any common node between any two loops, that means those are touching loops. If there is no common node between two loops like this, there is no common node between these two loops, so these are not touching loops. But as there is common node between these two loops, which one is common node? CDC, BCB. So common node is C. Here also C, here also C. So these two loops are touching at common node C. So loop 3 and loop 2 are touching loops. Likewise. So here, which are non-touching loop? See, this loop doesn't touch this loop. This loop does not touch this loop. That means this loop. This loop does not touch this loop. So this loop does not touch any of these three loops. These three loops are not being touched by this. So there are three isolated loops. One is G2H1 and G4H2. G2, another is G2H1 and G4G5H3. Last one is G2H1 and G4G6H3. So these three are non-touching loops. Now this loop touches this loop. Similarly, the pink loop touches this loop. So all these three loops, all the three loops present here touches each other. So there is no non-touching loop here. But this loop does not touch any of these three loops. So there will be pair of non-touching loops as this with all these three, which is mentioned here. Now, similarly, determine for this SFG, determine the possible forward path gains and loop gains. So how to determine that? See here. The input, which one is input net here? X1. As X1 is having only outgoing branches. X1 is not having any incoming branches. That is why X1 is input node. Similarly, X8 is output node. So what are the paths connecting X1 and X8? This path connects X1 and X8. So there is one possible forward path. So these are two possible forward paths, and another possible forward path is these three are three possible forward paths. So see here it is mentioned. This one is one forward. This one is one possible forward path. This one is another possible forward path, and this one is third possible forward path. So first forward path is having a gain of 1 into A32, A43, A54, A65, A78. So A32, A43, 54, 6, 65, and 7, 6. Okay. So these are forward path gain for this first forward path. For this 1 into A72 into 1. And sorry, 1 into A72 into 1. So A72 is another forward path gain. And third forward path gain is this 1 A42, A54, A65, A76, 1. So these three are three forward path gains. Next slide. What are the loop gains? How many loops are there? It's a complicated one. See, this is one loop. This is another loop. And this as a whole is a loop. So A3 to A23. one loop. A43, A34, another loop. Similarly, A54, A45, A65, 56, A76, A67. All these are loops. A77, another loop, which is known as self loop. Now, this one is a loop. A42, A34, A23. Similarly, see here, A57, A67, and 56. This is similarly, this is a loop which is being described here. But now see, this cannot be considered as a loop because this one cannot be considered as a loop because this is A57, this is direction of A57. Now this would have been a loop if its direction is here. So this is not a loop. What are other loops? A7 to A57, A45. A7 to A57, A45, A34, A23 together forms a loop. This comma will not be here. This comma will not be here. Another loop is A72. Another loop is A72, A57, this loop is considered. Okay. Another loop is A72, A67, A56, A45, A34, A23. So these are the possible loops. Now see, A32, A43, A34, A23, A32, A43, A34, A23 cannot be considered as a loop. Why? Because see here, this is the point which is repeated twice. So this node is repeated twice. When this forward path is encountered, this loop is encountered first time. Later when it comes through this, again it is encountered. So in a closed path, if a node is repeated twice, then it will not be considered as a loop. So this will not be a loop. This will not be a loop as X3 node is encountered twice. Similarly here, A65, 76, 67, 56 will not be considered as a loop because this loop X6 is encountered twice. So these are not loops. So these are the concepts of loops. Now let us discuss how can we draw SFG from describing equation of a system. So let us assume these are the equations of a system. So x2 equals to 1 to x1. So let us assume this is x1. If this is x1, this is also x1, because in between these two there is one transmitters. So both will be x1. Now x2 equals to what? A21 x1. So with x1, A12 will be multiplied. This is x2. So A12 multiplied by x1 will produce A12 x1. So this signal is A12 x1. Again, x2 is addition of A12 x1 and A32 x3. This is A32, this is x3. This point is x3. So x3 multiplied by A32 will enter at node x2 to validate this equation. So first see here, x2 is addition of 2, this signal and this signal. So x2 should be addition of this signal A12 multiplied by x1 and A32 multiplied by x3. So x3 multiplied by 3, A32. This equation is validated. Similarly, x3 is addition of this 3. So this is x1, this is x2, this is x3. x3 is addition of x1 in multiplied by A13. So from x1, one signal will be towards x3. So this is A13 x1 plus A23 x2. So x2 will be multiplied by A23. So this is A23. And x3 will be multiplied by A33. So there should be a self loop of A33. So this is how you can get SFG from the governing equation. X4 equals to what? A24 x4. So there should be a self loop A24. This should be x2. This should be x2. This subscript says there should be relation between 4 and 2. So x2 through A24 will enter at x4, and x3 through A34 will enter at x4. A34 through this will enter at x34. So today we'll end up here, and let me summarize the lesson of today's class. Today we discussed about what is SFG, why shall we study SFG, how can we use SFG to get overall transmittance of a system, what are the basic terminologies such as loop, node, loop gain, forward path gain, all these terminologies associated with signal flow graphs. And later we discussed about few examples that validate the concept of nodes, loops, loop gains, forward path gains, all this. And lastly, we discussed about how to get signal flow graph from governing equation. So any system may be represented by system equation, mathematical equations. From that mathematical equation, how to get SFG, aiming towards determination of overall transfer function, that is being discussed in today's class. So in next class, we'll be discussing about Mason's gain formula, and we'll apply Mason's gain formula to determine overall transmittance from signal flow graph. Thank you all for your patient hearing. We'll be meeting at next class. Thank you all.